Good morning, everyone, and welcome to KETIV's Autodesk Virtual Academy. My name is Eric Paul, the Marketing and Communications Coordinator here at KETIV. With me today is Nigel Mbayak, Application Engineer here and usual AVA host. Today he's going to be covering thermal simulation in Fusion 360.
Yep.
This is one of the topics that you guys requested. Fusion 360 can also do other types of simulation, and we'll touch on that a little bit later.
Well,
Nigel, do you want to tell us what it's going to be about today?
yeah, so we're going to go with a simple thermal simulation, just checking temperatures at equilibrium in a simple model. I'll kind of explain how this all came together first. But before that, I'd like to go ahead and mention that this was Richard Sanchez's baby, essentially, about a couple weeks ago. And Richard Sanchez was actually supposed to do this presentation, but he got tied up in some other commitments. But Rich decided he'd like to be on the call with us. So hello, Rich.
Hey guys, we're in Houston today. We're watching it to see what's going on, and we'll be here for any questions.
Yeah, so Rich is actually at a customer over in Arizona, I believe, Rich?
Yeah, Tucson, Arizona.
Perfect. Yeah, so thank you for letting me adopt your, essentially your baby here, and hopefully I do it justice. So we're going to go ahead and jump in the presentation. If you do have any questions, myself, Eric, and Rich will all be monitoring the questions via the questions panel. So if you do have any, go ahead and type them in, and we'll be able to address them during the session. So with that, let's get in here. So thermal simulation in Fusion 360. Let me just get my PowerPoint up here on my main screen. So essentially, what we started, if you look at the model here in the top right of your screen, this is one of the Autodesk Foundation customers, a similar model to one that they use. Essentially what they do is they build these polycarbonate shells that are heated for babies in less fortunate countries, and then they, correct me if I'm wrong, Rich, and then they hit them with UV rays to prevent jaundice, which is always good. You know, you don't want diseases and stuff.
Correct, that's right. This is one part of it, is the heated bassinet, and then there's a blue light that goes on top of it to prevent jaundice.
Perfect. All right, so just a little background on exactly what we're going to do. I guess you could also look at it as like some kind of crock pot or something if you really wanted to. I was thinking about doing the same. So what are we going to do today? We're going to teach you how to validate your designs using some of the built-in simulation tools in your CAD software. And this quote from the Fusion Simulation website, make great products by delivering better designs quickly. And we'll kind of show you how Fusion allows you to do that. You can kind of optimize your designs for temperature. You can optimize them for strength in certain places with some of the stress tools, among other things. So you can always make your designs better in that sense by, reinforcing areas of note that see a lot of stress or heat, et cetera, et cetera. So for those of you who don't already know what Fusion 360 is, well, Fusion 360 is another one of Autodesk's 3D CAD tools, similar to Inventor. Those of you who have current subscriptions to Autodesk software, you do have Fusion 360 available to you as a cloud tool, full-blown Fusion 360, not just a trial or anything. And it does multiple types of modeling. It does parametric, it does T-spline modeling, among a couple of others. It's also a CAM software for those people who are using, CNC machines to create prototypes of their parts or their parts, period. It also prints to almost all major 3D printers. And then it's also a simulation tool. So similar to Inventor, it does have some simulation capabilities built in. So among those simulation abilities, we're going to go over a little matrix a little bit later on all of the Autodesk simulation offerings, what they do, what their capabilities are, what they can't do compared to other ones. But this is just Fusion here in general. So Fusion does static stress, modal frequencies, which is your vibration and stuff, thermal, which is kind of self-explanatory, and thermal stress, also relatively self-explanatory. With that, we're going to go ahead and jump into the live demo here. Let me go ahead and pull up my demonstration. Perfect. So right here is the heated bassinet, or crock pot, or whatever you really want to call this. Obviously here at KETIV we don't condone cooking babies, so we want to make sure that this stays at an optimal temperature to keep them warm yet not be dangerous to to burning. So here in the in the Fusion taskbar, there's a couple of things you can do. So first you want to be able to open your model. I've already opened it, and Fusion is a cloud tool, so everything is stored on the cloud. You can also store everything locally. Fusion keeps track of revisions. You can open old versions of things. You can share things with other people using the built-in tools. It does use like the A360 drive, which is also available to people with current subscriptions. And so Rich actually shared this project to me last week, so Rich actually has access to this, and he can see any changes I make live on his end too, if he really wanted to. So you can you just open it from the panel here. This is kind of your A360 drive, and you can just go ahead and open any product. So this particular I open this particular model, and let's begin here. So once the model is open, you can jump into simulation mode here. So in Fusion, this is always my favorite quote from Rich Sanchez, you work from left to right. It's kind of like intuitive in that sense. They kind of really thought about how you're going to do this. So you're first going to go here on here. Most times you're going to be in model space, and then you're just going to want to go ahead and jump into the simulation space, which we already are in. Then you're going to want to create a study. So this is where you get those options on which kind of simulation you want to run. In this case, we want a thermal simulation. I've already clicked this and started one. So we don't have to start a new one. I already have one open right here. So like I mentioned, you want to move from left to right. So the first thing I'm going to do is define materials. Obviously, if you don't define materials properly, you're going to run into some issues, especially with thermal, where things have different thermal conductivity, different heat constants. You're going to have some issues there. So we're going to go ahead and select materials. Component 1, 2, 4, or sorry, there isn't a component 2 here. 1, 3, 4, and 5. So component 4, I'm going to go ahead and hide some of these guys here. Just to show you real quick, component 4 is actually the heating element. So that's going to be, that copper element that's connected to electricity that's heating this whole thing. So we're going to go ahead and jump into materials, and the rest of it's going to be polycarbonate, which is probably the closest material to what this thing's actually going to be. So 1, 3, and 5 are just the surrounding area. And in the original model, these two are already polycarbonate. We don't really have to change anything. Component 4, which is the heating element, is already copper. And component 5 looks like it was modeled as steel, so that wasn't changed in the actual part model itself. We're going to go ahead and change that with this drop-down here and go from as original. So Fusion has a full materials library similar to all your other CAD tools in Venner, among others. And we're going to go ahead and jump into polycarbonate. You could also, whoops, let's not do that. Let's change all of these to as original. Apologies, I accidentally highlighted them. So change these to as original, and then change this to polycarbonate. You can also type this in. You can type like PO, and it'll bring up polycarbonate or whatever starts with those two letters and run that way. So there are a couple of ways that this model was created. So if you look here at component 5, I'll turn that on. Component 5 is what directly surrounds the heating element. There are a couple of ways, the customer or, say I wanted to know what kind of material I wanted to put directly around the heating element, whether or not I wanted it to be encased in polycarbonate, or, I wanted there to be some air pocket in between, have it suspended in there some way, among other materials. You can do so by changing the materials here. I'll show you one later where this is air, so it's suspended, and you can see there's a small difference in the heat there. So next we're going to go into the loads. I'm not going to show you how to do all of the ones that I've applied here, but I'll jump into a couple of them. It'll just take too long. As I noted, it'll take me days to show you all of the simulation capabilities in Fusion. I don't even know them all myself. So definitely we'll try to do our best to see what we can cover here in about half an hour or so. And I'm just going to do this real quick. So we're going to go ahead and jump into our load options here. We're going to apply, let me turn everything on here real quick. And we're going to go ahead and apply, there's 5 types of thermal loads here. And if you hover over each of them, oh no, not here. If you hover over each of them here, you're going to get a flyout that says, what kind of load this is. in which case when you use this and whatnot. So we're going to go ahead and go with an internal heat here. And we know that this heating element, let's see, and we'll pull that from here. And we know that this heating element, internal heat value from the customer is about 60 watts. Whoops, that's 600. We don't want that. That's a few too many. Let me go ahead and edit this real quick. Oh, it's down here. Yeah, 600 watts, that might be a few too many. So we're going to go 60 watts. Then we're going to go and select the body. And then, so it's going to select that geometry, and it's going to give us this heat load. Perfect. So we have it over here. It's visible, and it's not suppressed. Second, we're going to turn on all of the other components as well, so we can see everything. Then we're going to run some, so there's some radiation here happening from the inner and outer shells. It's just how it works. So we're going to select all these faces. If you don't select this and you select a face, it'll only select that singular face. Let's move this. And if you select all and you select one, it should select the entire body, all the faces on that surface. And so we're going to do the inner surface and we're going to do the outer surface. We're going to run emissivity value of 1. We're going to temperature value of 20 degrees Celsius is the ambient, so about 68 degrees Fahrenheit. Seems to be pretty normal in an air-conditioned room or whatever. So we're going to have that. And then we're going to apply a temperature. Instead of me selecting all of these faces in the element, I already did it. I just don't want to spend the time doing it again. So I'm just going to turn that one on. I applied the temperature to 30 faces on the heating element here at the bottom. And then there's some convection too that we're going to be running between the interface, and then I got this convection value from the Googles. Actually, Richard Sanchez got it from the Google, so I have to thank Rich for that. So we're running this this convection value for coefficients, and then input type. You can do constant or temperature dependent, so it can change based on the temperature of the actual the location, which is kind of cool. And then same thing, ambient temperature 28 degrees. What this is going to do is going to account for all of the convection that we see with the model. And then there's another one here. We'll go ahead and turn that guy on. Once we're done with the loads, you can do a couple more if you wanted, depending on how exact you wanted to be with this model. It's pretty close between like this and then having like 5 more, which I added earlier. Those are actually in the final sim. I'm going to go ahead and go to contacts. So Fusion doesn't know how all of these bodies are connected, or if they're connected at all, especially because sometimes there's pockets in between them. And so you can manually select all of the contacts where they're bonded, or you could have it do automatic contacts, which is pretty nice. So what it does is it calculates all the contacts for the bodies that are connected to each other or overlap. So we're going to do that, and it should give us like 50, I think. So there's a bunch that I suppressed earlier. Oh, and they're still there. So I'm going to go ahead and enable all of these. There's a way to do this faster. There has to be. Anyways, I'm just going to jump. I'm not going to run this one actually. I'm going to run a different one, which I already had all of this stuff done. But after all of this, you're going to select all of these bonds. They're all going to be unsuppressed. And we're going to go ahead and jump into the green light. So the green light tells us we can solve. If you don't create any of this stuff, or there are things missing, you'll get a red or a yellow light, which I didn't notice until I was actually doing. I was actually running some of this. I was like, hey, the light changed to green. So there's another really important thing here in. Sorry, I need to scroll down here. In simulations in general is your mesh for FEA. You're going to want to make the mesh fine enough where you get all of the detail that you need, but not too coarse in which you don't get, or not too coarse in which you get all of the detail you need, but not too fine in which it takes too much computing power to actually solve this thing. So we're going to go ahead and jump into the meshing, and there's some meshing options here. So average element size, it kind of explains, and if you hover over here too, it explains like what kind of range you should be in. So average element size, we're going to jump to, it says between 5 and 10% is recommended. We're just going to jump on the higher range of that. It'll tell you, overly fine mesh is going to cause high energy consumption, or you can use adaptive mesh refinement to refine mesh in critical areas only. We're just going to go to 10, minimum element size, percentage average size. We're just going to jump on the lower range of that, which is 10. Actually, we're just going to jump to 20 here. Turn angle, smaller the angle, more elements generated on curves. So I'm just going to do something in the middle, 45, and then a grading factor of 1.5. You can create curved mesh elements to better follow the curved and rounded faces. You can. This last one is the element length is relative to each part bounding box rather than the entire assembly. So we're going to go ahead and hit OK here. And once this is all done, you can go ahead and start to run the results. Since not all of the stuff was bonded, I'm not actually going to use this one. I'm actually going to use a different one, which I ran earlier, which is here. So I'm going to go ahead and run this guy. Same model, same everything. And it's going to take a while depending on how fine that mesh is. So here, I didn't make it too fine.
While we're waiting this to solve, we got a question here from Paul asking, aren't you skewing your sim with an emissivity of 1? Sounds too high.
So, okay, well, first we'll answer that question from Paul. So it could be too high. That's kind of why when I'm running all of these sims, you need to look up the material properties and everything. You need to make sure you do your homework kind of in regards to constants and emissivity values and everything else in regards to radiation, because if you do put the values in wrong, you could get crazy results like this. This is expected because I made it this way on purpose. So the other thing to mention when you're doing simulation is kind of to give yourself a sanity check. We applied 100 degrees to the heating element here, and if you look, this whole thing is almost, it's high 90s or 100. And why is this? You look at this and you're like, you can't believe all of the sims that you do. In this case, there is a problem. If everything here was 97 degrees, you'd definitely run into some issues. So you can't believe everything you get out of the program. You have to make sure all of this. That's why this is the reasoning why your setup is really important. So actually, if you look here, I set the study material to copper, and if you look at this, I actually set this bounding box to copper, which is not what you want. We actually want polycarbonate. So definitely, this is just an example of what happens when the importance of applying the proper materials to your product or your simulation, because then you're going to get horrible results like this. If we run this again, we should get it to exactly where we want it, or about there based on the meshing. And then while this is running, we have another question here from Peter. I have an ultimate license for Fusion 360. How much simulation am I allowed under the credits per sim run? So all of the simulation in Fusion 360 is done, I guess, locally, not necessarily using the Autodesk cloud to compute everything. Kind of like things like CFD simulation, which you can use like cloud credits to run your simulation. This is all included in your Fusion license. You can even run this off the internet, I guess. I guess that's what you would call it, right? Yeah. And you have all the simulation capabilities. You don't need to really be connected to the cloud at all times. So hopefully that answers your question. So here, when we made the material correct, we kind of got some results that are somewhat desired. So let me turn off this slice panel here. So there are things you can do after you get results. You can go ahead and probe surfaces. You can probe points, and or you can create these slice panes. So these slice panes are really cool. We're going to go ahead and select this surface here. And then you can go ahead and drag this plane wherever you want. And what it's going to do is going to do like a section cut of your model. So I'm going to go ahead and just jump this in here about where one of these guys is, and we'll be able to see some stuff. All right, perfect. So we'll go ahead and set that up like that. So as you can see here, you have some results over here on the right-hand side. You can move these around wherever you want. You can either set temperature or heat flux. You can set this to Fahrenheit. We're in America, so we use Fahrenheit. And there's some more options here. So legend options, you can set the size of legends to be large if you really want to, or small. I usually keep it here. You can make it thin, which is pretty self-explanatory. You can change color transitioning to smooth or banded. So instead of getting this gradient of color, you can band it and it'll give you solid colors to where the temperature fits in this range. And then you can change the shading to default colors, shaded, or presentation. I usually do on presentation because doing presentation right now. So we're going to go ahead and go smooth, kind of gives me this nice gradient. And there are other things you can do here with the temperature legend over here. So this tells me how many nodes I have and how many elements I have. Obviously, the more elements and nodes you have, the longer it's going to take to compute something like this. I know that when I was in college, I was running CFD simulations with like millions upon millions of elements, and they would take my horrible, horrible computer multiple hours if it didn't crash. But that's beyond the point. Anyways, so you can do some stuff here. You can go ahead and drag these to get more range here, or not more range, but you can get more numbers here in the range. You can go ahead and take these arrows here, and you can drag those up to get rid of any areas in which the range isn't selected. So if we get rid of all the cold areas here, we can start getting into where the warmer areas are. And you can do the same the other direction. So we'll do this. You can take everything from hot to cold. So it's going to start taking away all of this all the way down. And you have some other options here. If you select this, it sends the legend away, and you get some information, some basic information about the thresholds, which is the range in which the temperatures lie, the minimum, the maximum. So the minimum is 68. Why? Because that's the ambient temperature we set for this whole this room, I guess, is what you could say, putting this thing in. And then the max is 100. That's what we applied to the heat, the heating unit, I guess, is what I want to call it. What else do you have here in results? You can go ahead and export. Let's see here. You can export reports. That gives you a report summarizing some of your simulation results. So I'll go ahead and click that. And you can send these out as like PNGs and stuff. You can write stuff in the summaries. You can send the pictures through. A couple of other things as well. So you can preview this real quick. It's down here. So this kind of shows you what's in there. It shows you what options you created, what materials you used, pretty much all of that stuff. It shows you some of the material properties of the units you selected, some loads, and it's going to show you everything all the way down to the bottom. So that's definitely of use if you need to send that to somebody else. We do have a follow-up question from Peter here. So I guess I did answer Peter's question. And the next question would have been CFD. So CFD you can use for full-blown Autodesk CFD. You can use the cloud to do your solving for you. Say you're using multiple millions of elements, like I said before. You use these things called cloud credits to run those simulations in the Autodesk cloud. So your computer is not being taxed. It's going to be cloud's being taxed for the computational power. And you don't do that in Fusion 360. Most of the models you're going to use in here aren't going to be millions upon millions of elements unless you've got some kind of supercomputer, I guess. Let's see what else we have. I think that's it. We can create point probes. I'll show you how to do that real quick. Or surface probes if we want to do surface. It tells you, how hot these surfaces are. This is the top surface. That's not what I want. I want this surface. So, you can kind of put these here, and they stay here if you do run the simulation again with different settings. So they'll update. You can figure out, oh, like, hey, this is a point of note here. It's at 96 degrees, which is obviously not very good for children. And, we can do that. So I did change some of this model in another simulation. I'll go over really quick. Study 3 over here is just another study. Similar to that one, and I got different results here. So this area is actually going to be, we'll go ahead and probe this real quick. And it should be something like 85 degrees, which is pretty tolerable. And why is there a difference here? So the difference I made here is if you look at the model, go to the home view here real quick, or I'll just rotate this guy. If you look here at the model, Okay, if you go here and look at the heating element and the surrounding area, in the original model we created that as polycarbonate. And so there was some conductivity between the copper and that polycarbonate, so there was obviously heat transfer there. In this second one, we assumed like, hey, let's go ahead and suspend this heating element in the middle of, in between these two shells of polycarbonate. So there's an air pocket here in between the two. And that's what we ran in the second simulation. Obviously, you can't have it suspending there, like defying gravity. There's going to have to be some way to connect it. We didn't model that in yet. We just wanted to see whether or not this would make a huge difference, and it did. Instead of getting temperatures in the 96s at the top, we're getting temperatures like 86, which is less dangerous to whatever you wanted to do. So, say for example, you wanted to cook a chicken in here. Sure, you could have it at 96, or you could use full polycarbonate and have it travel through, or even use things like stainless steel and stuff to get that conductivity higher. But it's the same concept. So if you did want to copy this study like I did and then run it with different materials without getting rid of the first one, you can do so. So if you right-click up here in the study, you can clone it, you can delete it, you can do pre-checks, or you can even solve here. So if you clone this, what it'll do is in the same window, it'll just run another study. Everything will be exactly the same, even the results. So if you go in here, you want to see what happens when you refine your mesh without getting rid of the original study, you can do so by just cloning it, and then you can, if you click this and you wait long enough, it'll give you the option to change this. So I can change this to finer mesh, for example, and then I can just jump into the meshing options and just make these numbers smaller or as desired. We do have a couple of other questions here. From Radu, could you create study 4 without losing study 3? I like having multiple scenarios at the same time. So yes, I just did that. Hopefully that answered your question, Radu. So yeah, the only reason that I ran into this one from this original one is because this one wasn't fully set up when I was creating the parameters here. But yes, you can have multiples. This is one assembly and study file that is independent from any of these other ones. So this one has its own model, this one has its own model, this one has its own model. Even though the models are the same, they're 3 different files in the cloud. Let's see, and Adam Estrada asked another question here. Eric, can you read that for me?
Sure. When applying the thermal load, what other values can be input? BTU, temperature, etc.
Yeah, so when you are applying loads, you can override the units when you're applying stuff. So if you go to apply temperature, you can apply actual applied temperature at those points if you wanted to, or if you wanted to go in something like the internal heat. Let me go ahead and edit this real quick. Perfect. You can change this from watts to override the units. You can go to BTUs per second, joules per second. All of the major imperial and metric units are in here, even with the constants as well. So for some of the heat constants that you're going to input, you're going to be able to change the units as desired. You don't necessarily have to go to Google and have to translate coefficients into millimeters squared instead of meters squared, stuff like that. So from here, we're just going to go ahead and jump back into our PowerPoint. Obviously, I can't show you all of the capabilities of the simulation in 30 minutes. It's kind of impossible. Just there's so much stuff. We only jumped into thermal today, and I didn't even show you everything that's possible. Like I said, there's still static, modal, and thermal stress to go over, which we might go over in some future webcasts here. So just make sure you fill out that survey there at the end when you exit the webinar, and you can go ahead and mention what you want to see next. If you want to see more Fusion, I know we're doing Fusion Chem in the future, and we're doing a couple of other things as well. So let me go ahead and jump forward here. So this, I made this. Sorry if the red is hard on the eyes. This is kind of a capabilities matrix of all of the products that Autodesk has in regards to simulation and their capabilities. Everything with a green check mark, it does. Everything with red X, it doesn't do. So if you note here, a lot of people are using, a lot of people here I know have Inventor, or they have product design suites, or I guess moving forward you're going to have product design collections. Just to note, Inventor doesn't do thermal. That's just something Inventor doesn't do. So if you want to do thermal, there are capabilities in Fusion to do so. But what Fusion doesn't have is it doesn't have Inventor associativity. So if all of your parts are created in Inventor, and you're kind of creating those assemblies in Inventor, the translation isn't seamless between Inventor to Fusion. For Inventor, things like SimMechanical and Nastran InCAD, which is like not built into Inventor, but it's like an add-in into the Inventor software. Those have Inventor associativity. It's pretty easy to go from Inventor straight into those tools. And as noted, CFD, you can do some thermal in CFD, not all of it, but obviously CFD is in CFD, and things like plastic injection molding are done in MoldFlow, so you can simulate, your injection mold and where the, my gosh, I can't even remember what they're called. Anyways, you can figure out which directions the grains are going to be when you're doing your injection molding, and then you can run the simulation on top of that to find weak points and stuff like that. So we're going to have a couple of other questions, but I'm going to go over a summary real quick. Just to remind you, if you do have any questions, go ahead and type them in. We'll definitely answer them. So summary, you want to leverage the available tools to create better products quickly and efficiently. As subscription customers or current maintenance plan customers, you do have access to things like Fusion. You do have access to other cloud tools like cloud computing and tools such as A360 to store your data. So definitely use those available tools to you to quicken your workflows and make them a little bit more efficient. And two, ensure that your product works at safe operating temperature / prevent catastrophic failure. So in this case, if you want to make sure that you're making the particular components out of the proper material, or else you're going to run into some some heat failures in regards to burning children. Definitely not good, or burning whatever you want to put in there. So with that, we're going to go ahead and jump into Q&A, but before that, we do have, for those of you who are interested in more simulation, we have some other webcasts. So this webcast is happening on Friday, September 9th, and this is design and document skid-based processing equipment, where, look, Jorge Fernandez actually going to be there, RNO. This is first webcast for RNO. And they're going to demonstrate some of the Nastran InCAD capabilities with some skid design. So if you want to, look at that, I think it's going to be mostly stress-based. If you want to look at that, definitely sign up. You're not going to receive the notification automatically if you're signed up for AVA, because this is a completely separate webcast. What I'm going to go ahead and do is I'm going to copy and paste this into the chat box. All right, so with that, I'm going to go ahead and jump into Q&A. We do have a couple of questions. If you do have more, please send them in. We'll definitely answer those. Let me jump to that. Also, questions at KETIV here. Eric, if you want to explain, that's pretty much like the end-all, be-all. If you have any questions at all.
Yeah, anything you ever have, just send it to questions at KETIV, and we'll get it. We'll send it to the right people. We'll get back to you. Real easy.
Yeah, if you don't know who you want to send something to or what department you need to send it to, it'll get sorted in questions. Or you can call that number, and one of our receptionists will take care of you. That's not a problem.
Yep. So it looks like we have a few more questions here. Andrew's asking, with the air filler or other fluids, does the thermal sim take into account fluid dynamics? So
yes, it will. It'll take into account at some level, not necessarily the same as something like CFD would. It is taking into effect some of that airflow in that pocket if you wanted to create it that way. If you set the simulation up like that. So obviously, if you don't create the proper loads, you don't create the proper contacts and stuff, you could run into issues of it not doing that. It doesn't account for too much change. I actually tried it. I think we got a difference of like, I don't remember how much it was, but it was within 5%. Nothing too crazy. All right.
Another question here: is Fusion sufficiently capable to accommodate a baby model additional heat source? So besides the element having another heat source of the baby inside the bassinet.
Yeah, so you can. I could have applied temperature at the top. I don't have a model for a baby or a chicken. I kind of wanted to create a chicken model. Show there's some conductivity from the chicken, and here's some radiation from whatever's in there. Yeah, you can do as much stuff as you want. Obviously, the more complex the model becomes, the more taxed your computer is going to be in regards to processing that data. So today I ran some pretty coarse meshes. I did run some fine ones yesterday, and it took my computer a couple minutes to solve some of them. Today we're in the range of around 50,000 elements, I believe, and yesterday I was running stuff at about 500,000. So it was a ton more. It was actually like way smaller than the suggested range that Fusion gave. I just wanted to see its capabilities, and it was pretty accurate even at that 50,000 as opposed to that 500,000. It was within like a degree or two, not even, in some areas, so nothing too crazy.
All right, looks like we answered most of the questions during the presentation, so I think that looks like that's it for today.
Yeah, definitely. Apologies for any confusion I may have caused. I'm sure Rich would have probably done a better job, but I did my best. Anyways, if you do want to see this recording or any of our other recordings, they are available on KETIV.com, or sorry, youtube.com/KETIV Technologies. Mm-hmm. Or you can just go on YouTube and search KETIV, and you'll be able to find all our videos there. Next week, we're doing a presentation on some of the most common issues that we see people on Lifeline. So I'm on the Lifeline team here at KETIV. If you guys don't know what that is, a lot of you guys do call for Lifeline. I see a lot of these names are pretty familiar. That's our support team here at KETIV. We have a dozen techs at a time, kind of monitoring the queue. And we do answer any questions or some troubleshooting for people who have problems. We get some issues over and over again. So for example, I'm sure some of you in the chat here have seen it before. You can get a Vault tab in your Inventor that's grayed out, so you have like no options. And we get that like once a week. So it's pretty common. We're going to go over the most common things and how to avoid them. So if you want to know, you want to avoid giving us a phone call. Obviously, we do welcome any phone calls, but if you don't want to spend that 30 minutes having to try to figure out what's going on here, the most common things we've kind of figured out, we're going to document those and show them to you next week. Yep. I think that's it. So for those of you who want to join that webcast next Friday, 2 Fridays from now?
2 Fridays from now, September 9th.
2 Fridays from now, please do so. That week we actually have 3 webcasts. You'll be receiving some of those notifications via your AVA emails. But yeah, so with that, I think that is all. So thank you, Eric, for being here.
Yeah, thank you, Nigel, for the presentation.
Thank you, Rich. I know he's listening. He might not be able to speak right now, so I'm going to thank you all.
I'm here. You guys did a great job.
Thanks, Rich. No problem. Have fun in Arizona. And everybody, you have a great weekend. I guess have a great Friday first, and then have a great weekend.